Alrighty, let's see how we can define mathematically the concrete state space for refinement number 2, M2. Remember, there are always two parts for the model that you may want to think about: static versus dynamic. In the case of static, we may have to introduce maybe some new constants and their associated axioms. We'll see. Static part is going to be color, because we want to make sure the set of state values for each traffic lights should be either red or green, but that one together should be a type called color. So the sets over here is more like a carrier set, which we introduced already in lab number 1. So you can review your lab number 1 about what a carrier set is. But it's simply just a set. Exactly what members should be in the carrier set, we're going to define them as axioms, which we'll see. And we introduce two new constants, red and also green. And what about the axiom? Both are actually important over here. Axiom number 1, and just notice the naming convention. We're talking about axiom for M2, so that's why you see the 2 over here. And axiom number 1 and axiom number 2. The first one is to define exactly what color carrier set should be. We are using a set numeration notation here. We're saying color has exactly cardinality 2 in containing green and also red. These two members, but we want to make sure these two members are distinct. They cannot be duplicated. In that case, there'll be green not equal to red. So we're making sure each traffic light is going to switch between red and green, two distinct states for their values for regulating the traffic. What about the dynamic part? In that case, we're going to use the so-called superposition refinement scheme, which we spoke about before. Basically, whenever you use a superposition, that means you're going to inherit whatever variables from the abstract model, and then you're going to introduce some new variable as well. And the concrete and abstract variables should be used together. So you can think about they are all concrete at the same time. Right, so this will be the diagram we already went over. Let's go over some bullet points just to recall. And then we'll do some exercises to define the invariants together. So the abstract variables from M1, right? You can see from M1, A, B, and C are now considered as abstract because M1 is more abstract than the current refinement M2. They are actually still in use for M2. So A, B, and C, you should really consider them as still like a valid variables in the current refinement M2. Meaning that in the guards and actions for the events that we're going to talk about, you will see A, B, and C will still be manipulated. And we also got two new concrete variables that are introduced, MLTL over here and also ILTL over here. And you really want to contrast this refinement mechanism when we actually go from M0 to M1, in which case we replace the abstract variable from M0 called N by A, B, and C. So that means in the case of M1, we don't really try to update the variable N, which has been replaced by A, B, and C. Right? It's a very important distinction you want to make. And remember the diagram I drew earlier. You really want to make sure you understand how to do the refinement step. Refinement scheme should be applied from M0 to M1 and also from M1 to M2. Right? It's a little bit of repetition here, but it's really important to emphasize. Let's now try to do some exercises. Given the variables are these A, B, C, MLTL, ILTL, we got 5 variables in the concrete state space for M2. What should be the invariants? Well, the first two invariants are simply the so-called typing constraint. We're saying that MLTL, ILTL, so these are just traffic lights, meaning that they should be, the value of each light should be one of the distinct states, which should be either green or red. That one's straightforward. What about invariant number 3 and also invariant number 4? These are the two conditions I would like you to derive on your own before you compare your answer with mine as exercises, but I'll give you some hints. Let's now switch. Let me first of all set up the context, and then you can pause the video and do the exercises before you move on. We got the 5 variables, remember superposition. And also we got the 2 typing constraint invariants, and these are the 2 I'm going to describe informally to you, and I'll let you do the formulation. We got for the static part, we got the carrier set, we got the constants, and also we got the axioms. You can definitely refer to any of the variables and also any of the constants in your invariant conditions as your answer. Let's now talk about invariants 3 and 4. They are kind of symmetric to each other. So once you know about one, the other one should be rather straightforward. But I'll give you some intuition over here. Let's read it together. The hints will be for invariant 3. Being allowed to exit the mainland means 2 things. Number 1, the cars should be limited somehow, and also there should be no crash. think about there is one car over here that's about to actually exit from the mainland. If it is allowed to do so, that should be regulated by the traffic light over here. If they are allowed to really exit from the mainland, that must mean two things. Number one, there should be no opposite traffic, otherwise there will be a crash. Number two, it should be that adding this particular car into the breach, the total number of the cars on the breach and also on the island should still be limited, should still be bounded by the maximum, which we declare as a constant d from the initial model. So that'll be the hints for this invariant number 3. And number 2 exercise will be invariant number 4. It will be kind of similar. Let's say there is one car wanting to exit from the island and go onto the breach. It should only be allowed if the following, if it is allowed. That means the following should be true. Number 1, there should be no opposite traffic like before. And number 2, it should be that there is at least one car in the island. Otherwise, how can a car exit from the island? Right? So number 2, in some way, over here is a little bit simpler. But I think put more thoughts into number 3 over here, especially pay special attention to about inequality when you put the equation, when you put the predicates. All right, so now you can pause the video and then resume when you are ready to compare your answer with mine. Okay, you can now pause the video. Alrighty, so hopefully you got some answer on your paper. Let's now compare your answer with mine. Let's take a look. Why don't I do number 4? I think number 4 is a little bit more straightforward. Okay, what about I do number 4 first? Number 4, let me put a star over here. And number 4, based on the hints, if we're allowed to really exit from the island, so this will be regulated by this particular traffic light. What does it really mean when it is allowed to really have a car being able to exit from the island? That means the traffic light color must be green. So for star over here, I'm going to say if IL is equal to green. So this equation here is formulating being allowed to exit from the island, right? You want to really get an ability to really translate what formulates informal description into predicates. It is also a very important technique from this course. Means two things. There should be some car in the island, otherwise there's really no way for us to exit from the island. If you got an empty island with no cars, how can a car exit from the island, right? And also there should be no crash from the opposite. And apparently we got the variables b and a over here to be handy. So that's why a, b, and c should still be valid variables for this particular refinement number 2. So that's why we are using superposition rather than replacing a, b, and c by just ml and tl, right? MLTL and ILTL, of course. Right? So how do we make it conditional? We're saying that if this predicate over here is actually true, that must mean, we can use implies over here, right? Hopefully you already thought about a logical operator when you saw the hints. That means some car in the island, that means B over here should be strictly larger than 0. And no crash. That means the opposite side over here should be none. There should be no traffic from the opposite side. A is equal to 0. Hopefully you got this right. So this will be the answer for invariance 2-4. What about invariant 2-3? There is a little bit tricky about the inequality, which I'm going to talk about, but let's be careful. Okay, let me put star over here. For star, being allowed to exit the mainland, which should be regulated by this particular traffic light, MLTL. So what does it really mean? It is allowed to exit from the for the car to really exit from the mainland. So that means this should be green. So MLTL equals green. That implies what? Limited cars and also no crash over here. What about limited cars? Let me put something that might seem to be correct, but it's not exactly right. What if I put A over here and also B over here? So these are the two important quantities to measure how many cars are on the breach heading to the island and also how many cars on the island already. The summation of these two must be bounded. What if I put A plus B less than or equal to D? Let me put it at, and also no crash. That means the opposite side over here should be no car. C equals 0. This one over here is almost right, except for the less than or equal to. This part over here. This is arguably incorrect. Let me tell you the argument why it is incorrect. If this is this includes the possibility of equal to. If, let's say this. Remember we're saying that if the green light is actually over here, right? If this is green lights and a car is just about to actually go onto the bridge. If at the moment, let me just try to make this more visual. Let's say there is one car. Let's say this is the car which is about to leave the main lane. A car about to leave the main lane. And let's say at the moment, the traffic lights MLTL over here is actually green, right? Let's say it is green, right? It is green, right? Exactly the condition over here. It is green. However, we are saying that it is okay to have A plus B equals D if we allow that. In this case, A plus B equals D. But the problem is the current car that's actually waiting hasn't really got onto the bridge just yet. What if it follows the signal being green and really goes onto the bridge? What's going to happen? What's going to happen is the A over here is going to become A plus 1 and then plus B. What's going to happen? Well, it's a very, well, we can use arithmetic property very easily. If A plus B is already equal to D, what if I say plus 1? That's guaranteed is going to be strictly larger than D. So this is really a violation. A violation of the capacity requirements. Right? Let me just emphasize again, it's really important for you to rewind what I just explained if you need it. When you actually consider what it really means when the traffic light is actually green, it must mean that the current car might still go onto the bridge. And if the current car might still go onto the bridge, that means we're going to add 1 to the current value for A. So that if you say A plus B less than or equal to D as a current constraint, that's not good. Because when A plus B is exactly equal to D, adding the new car, passing a signal, in that case, you're going to get a violation. So that's why it's not good. Well, how do we fix it? The way to fix it will be, we want to say this one over here should be the following instead. This one should be fixed into A plus B strictly less than D. That should be the answer. Right? So this one here, that's why I said it's a little bit trickier. You really want to make sure it's very subtle, but the boundary case ought to be precisely right. Right? So what we have eventually are these two invariants. So invariant 2, 3 would be this condition over here. It's conditional, right? We say it's conditional invariance. Okay, this will be 1. And the other one will be, let me use yellow. MLTL equals green implies A plus B strictly less than D, and also C equals 0. So these are the two exercises solution. Right? Make sure you actually understand them. We're going to use these two invariants. We're going to take them for granted once we move to the later part of the lecture.